Okay, everybody, welcome to the pump sizing tutorial. We are going to size one, maybe two pumps, see how fast we can get through this, how much tape we have. I think what I thought I'd just quickly show you is the 3D model first. So we had this Google SketchUp model, and I hit File, Preview in Google Earth, so you can do that and pop it up in Google Earth. I'm not sure whether that works on our cluster computers or not, but we also have on the wiki the Google Earth version right here. So if you're wanting to get a little bit of a reference of where things are, it's good to check it out in Google Earth. So James has very kindly built our 3D model here, and so all the equipment that we're interested in is essentially down in here, and we'll probably work with the Google SketchUp model a little bit more because it's labeled a little bit better and it's easier to do measurements and things like that. But you can also do measurements on here. I assume you guys know that you can lay things on and do that and get distances right on Google Earth. That's kind of handy. We have put a kind of a fake version of their stack. Obviously it's not their stack, but it's in roughly the right location. Yeah, there's the stack right there. So it's in roughly the right location. And also I have, I'm probably wrong about this, but I'm guessing that their raw water pumps are either here or here. And I just arbitrarily kind of put our raw water pumps right here. So I'm not sure about that, but it seems like a reasonable place to put them. And so we're going to be interested in how we're going to get our raw water there, and then over to our facility over here. This is the DAF unit, I think, right, James? Yeah. And the ponds are basically here. So there's a little bit of, good thing about Google Earth is there's a little bit of terrain built into the model. So I guess it would be handy if we really wanted to try and get some of the elevations off here, but I'm not sure how to do that. So anyway, let's go and look at the model that we're dealing with here. So we need to pop up the VDI. Okay. And just resize that. So you guys are going to be responsible for these pumps out here. And I'm going to take a stab at this pump right here, which is the water feed pump. So that's what we're going to do first. Whoops. I can get it zoomed in there. So we're going to need to know some flow rates. We need to draw a sketch and all that good stuff. Probably the best thing to do is to actually start with a sketch. And let's do that. This might be a fairly simple and fairly fast pump, I'm not sure. So let's see, we have our pump here. And since that water is going to be pulling from the lake, essentially what we're going to have to do is put it, it's down, we've decided we're going to put it down by the lake. So it's essentially going to come down into a, I'd say probably it's going to be like a wet well. So there'll be a water level there. And then this will likely have an intake back into Lake Ontario. Now, I haven't done a lot of raw water pumps like this, but I know from past experience there was a big problem with zebra mussels, and so usually what they did is they did a little bit of, I think it was sodium hypochlorite injection back out here, and that eliminated the zebra mussel issues. That might be a bit of a problem with our algae though. So I think we'll have to kind of table that as an issue that needs to be resolved at some point in time, whether we put any sort of zebra mussel treatment facility in here or not. For now, I think we can just basically deal with the fact that we've got a pit that we can draw water out of for the pump. There's actually some good stuff on the internet on pump suctions for these situations. There's a lot of, because the flow rates are high and you don't want to have cavitation and suck stuff up into the pump, they have some really good guidelines around dimensions for pump suctions there. Gould's is a good reference for that. And let's see, I almost need somebody's P&ID here. I'm going to make some educated guesses here. One of them is that there's probably going to be multiple pumps here. So I can imagine there being 2, maybe even 3 pumps providing this service. I'm not going to worry too much about it in terms of the hydraulics. I just need to know it. I just need to know about it. Let's see. Just thinking about this as I go here. Probably strainers and things like that. And we've got our destination really is the Raceway Ponds. So that is, it's going to draw an open pit like that. There's going to be an elevation change. Actually, you know what I'm going to do? I'm going to just draw it a little bit up just so I can kind of show my elevation change a little bit. That's going to be a little tricky to try and get the elevation change out of that. Okay, and there's a whole bunch of other things rolling in here, like ammonia. So, let's see. Essentially, we're just going to dump it right into the ponds, I think. If we don't dump it into the ponds, then what we could do is we could bring it back into the Raceway return system, which is near the DAF unit. Let's see. Oh, this is going to get entertaining as it is. Okay, Raceway return. And we're probably wanting to bring the ammonia in there as well. So let's bring the ammonia in. I don't think it matters at this point in time where it's coming in. NH3. So you guys would have had to have had some sort of control valve on this. The Raceway return is going to, you can't really control the Raceway return. That's going to basically be coming back from the DAF unit. So we pretty much have to take, the majority of the water is probably in the Raceway return. And then this is really just handling evaporation and losses and stuff like that. So if that's the case, I put the ammonia in the wrong spot. Okay, so the ammonia's got to come in here. Okay. We're trying more of a PID than anything else. Okay, so there will be some sort of flow measurement here. I think I saw this on some PIDs. And essentially what people are doing, I think, is controlling the flow here in order to get a total flow going into the ponds. So so this has probably got an FIC on it. Okay, like that, and an FE. That, DCS like that, and I suspect we either have a total flow measurement here. I guess it could be done like that actually. Maybe that would be the best way to do it. Put a total flow measurement on here, and an FIC like that, and then just put a software signal in there like that, so that we get a total flow measurement. And if this one is low, oh, if that's the case, we don't need this. There we go. We just do it like that. Okay. I still think I'd want to have a flow measurement there. I would totally want a flow measurement there. Okay, I'm changing my mind left, right, and center here. Okay. I want to know how much water I'm pulling out of the lake. So even if I don't control it, I'm going to have a flow indicator there. Okay, that makes sense. So we've got a total flow going into the ponds. It's the Raceway return is basically sending us what we need, and in order to make that total flow, we're making it up with that flow valve there, and we're measuring what the total flow is that we're bringing out of the lake. That'll work. Anybody have any other suggestions or thoughts on what their PIDs look like? Did I miss any features? Would we use multiple injections for the ponds? Yeah, definitely there's multiple injections for the ponds. Yeah, yeah, this is, This is going to however many raceways we have for sure, Josh. Yeah, yeah. So we'll need to think about that. Probably what we could do is, this could become a complicated analysis if we tried to do every single, like analyze the pressure drop between everything, but we could also just look at the furthest place we've got to pump stuff and make sure we can pump the right flow rate up to that raceway. Yep, this could get interesting. And I thought it was going to be simple. I think that's pretty much it. If we need to add to the diagram as we go, that's fine. I guess what we do is this is Lake Ontario. The elevation up to the pump, I don't know. I'm going to say it's probably about 10 feet. We haven't really got a design for this, but it's probably about 10 feet of lift. We might, there are ways actually of building this and having the pump down in a sort of a dry pit here so that you actually don't have to pull out of the, you don't have to pull upwards, you just go straight into the pump. So if we find ourselves getting into problems with NPSH, we may want to rethink that one. And then we're going to want to know the distance from here up to the ponds, and I'm not sure we can pull that out of the model very easily. I'm not sure I'm good enough at Google SketchUp, but basically we may need to bring the water up as far as here. It looks like that's the highest point in the ground, and how good are people with Google Earth in terms of getting elevation? See how low. Says the elevation is 326 feet there. I'm just reading this number down here at the bottom right. 326 there. Whoa! Stop. Darn. Oops. There we go. We're getting warmer. Okay, 326. Let's see if we can get the elevation here. Ah, that's pretty good. 282. This one here is what I'm reading. Oh, you think it's this one here? Yeah, maybe. That one doesn't change. Okay, so wait a second. Okay, that was, I forgot the numbers. I should have written down. Hang on. That one said 282. What was the other number, you guys? 326. Yeah, I was just trying to put myself right on the surface. Okay, so that says 262. Let's see if we can. Maybe you guys are right. Maybe you just need to click on it. We can get the actual. Oh yeah. Whoa. Stop. $310. Maybe we can rely on that. That might work actually. So that says it's 308. 308 there. Yeah, that looks like it could be. Okay, so 309 there, and 225 at the water. Huh. There, we learned something new about Google Earth. Sweet. Okay, so this is elevation 225 feet. And this was basically 310. That should work. So, really? That's quite a bit of distance, isn't it? Why am I having trouble believing that? There's really that much distance? 306. 236. Oh, wait a minute. That says 254. 241. Oh, wait a minute. There's something. Oh, you know what? It's going right down to the bath. Okay, wait. We want to pick it right there. Yeah. Okay, that's about 263. Yeah, that makes more sense. Okay, so this is 263 on the ground, and the water level is going to be about 10 feet below that. Okay, so that, I'm starting to believe that a little bit more. 40 feet of elevation, yeah, I can believe that, maybe. So this is 253. Okay, do we have, now the other thing we need is, we're going to need some distances and things like that. So my trick for distances and such is to start drawing some, let's see if we can do this fairly quickly here. A little rusty with Google SketchUp here. Okay, so there's our water feed pump there. And we need to run a line, I think we'll probably just try and run the line straight up from the water. So what you need is, the trick here is as you move the cursor around, you're going to get 3 axes that it locks on. The blue is the vertical. The green, I think, is heading north-south. Once you kind of get it locked on the axis, you hold the shift key down and it kind of goes bold there. And then you can basically force, then it'll just stay locked on there. And then you can move out here and you say, well, we think we want to go about as far north as the stack for now. So we'll go right up to the plant. And then we'll pop up vertically. And what we want to do is we may want to move up, say, about 30 or 40 feet. So we're kind of, we have some road clearance. So I'm typing in 40 apostrophe. That gives me 40 feet of elevation. And then I'm going to go red. And what I need to do is I'm holding the center mouse key down and the shift key. That way I can actually move the model around. Okay. I want to be on the red axis to move east-west. Hold the shift key down now that I got locked. And now maybe this would have to run underground. That might actually be something that would have to be done. But the distances will probably be about right. Okay, so I'm going to run to the edge of the stack and then I'm going to drop down to the ground. Down to the ground. Blue. And I went down 40 feet. Like that. Whoa. Whoops, 40 feet. Okay, that gives me that. So I should be basically on ground level. Oh, the ground is sloping up on me. Okay, and hold the shift key down. And I want to basically get onto my pipe bridge here. So we'll run out to about there. Should get me onto the pipe bridge, roughly. Okay. Get the shift key on there. Oh, for some reason I screwed up a little bit there. Okay. And actually, if we ran it all the way underground, there's the DAF building there. Would we tie into the DAF building? No, we basically have to run right all the way up to the ponds, don't we? Okay, so let's zoom out a little bit here. Okay, why don't we run all the way up here? Whoops, green, green, green. There's a green axis there. We'll run all the way up here. And we probably need to run all the way across here. Whoops. We need to run all the way across here too, probably. Okay. Okay, so that's kind of my line length there. And if we want to know how much distance there is there, we can either put some dimensions on it like this. Oops. Come on. There. Okay, got that distance there. And that was going down into where? vertical line there. I know it's 40 feet because I actually typed it in. Come on, you dumb thing. There, come on. Oh, so close. Oh. There. Okay. And we're done with the water feed pump. Okay, so we just need to add those numbers up to get our line lengths. So we have 344. I just want to write this down here. 344, 12 in vertical, 216. Another 12 meters going down, 274 across. And then 148. And we're going to need to add a little bit of sort of engineering judgment numbers in here. Okay. And we've got basically, wow, there, 2,563, 1055. Okay, who wants to add those up for me? Who's got a calculator? Josh is busy. Do you want to use sponsored by Hewlett Packard? What'd you get? 602 meters? Okay. We're going to need to add a little bit in there, I'm sure, but so that's our discharge line. So we're good there. This is just going to be fairly short through here. This should go fairly well. Okay. So let's just pop up the wiki and just follow our instructions for doing this. Let's see. Trying to find my instructions. Of course, I can't find them. There we go. Okay, draw a diagram, determine the flow rate. So let's get the flow rate. We need the VDI for the flow rate. And of course, it locked me out. Everybody saw my password there? Good. Okay, so our mass flow rate there is 40,000 kilograms an hour. So number one is the diagram. Number two is what's the flow rate. Okay. That's the nominal flow rate. Now our rules of thumb would tell us that we need to add a little bit to that. So we might want to multiply that by 1.2 is going to be a big number. That would be a lot. That'd be a lot to add that to. Our rules of thumb say to multiply 1.2 onto that, right? And then, since we have a control valve on here, we want to have a minimum flow bypass. So we probably want to spin that. I'm going to do this the way I think all pumps should be done generally, but I have a feeling that because this is such a big pump and it's such a specialized sort of application, there might be some different rules of thumbs for these for this pump. So I'd want to go back and check some of these little engineering thoughts here. Well, let's do it this way. Okay, so we're going to say this is 15% of the flow. So essentially what we do is divide that by 1 minus 0.15. And that gives us Somebody want to check my numbers at the same time? $56,500 kgs an hour. So you remember we said we're kind of justifying this whole idea of a process based on the fact that we have a freely available source of water. So when we go and do the economic analysis, normally what we would do is we have like a cost for various utilities. I think this one we're basically making our own utility. So our cost is having to buy the pump, run the piping, and electricity, and build the facility and stuff like that. We're basically going to include that in our capital estimate and the electricity in our operating cost estimate, and we won't have to actually have a line item in there for the cost of the water, because we basically built it here. Okay, so 56,500 kgs an hour. I'm just going to convert that into US gallons per minute by first multiplying it by 2.046 to give me it in pounds per hour. So that's 124,500 pounds per hour. And if I divide that 500, that's actually it's not that big a flow rate. It's only 250 US gallons per minute. 249. Oh, that's not that big. Surprised it's that small, actually. Just look like big numbers initially. Okay. So we have our flow rate. Next is to get the inlet pressure. So what we have is we have essentially atmospheric pressure less the line losses here. If you what I did yesterday in class was basically ignore the frictional losses. I think it's pretty close to that. So if we assume the source pressure, that pressure is 0 psig. If we want to size a line and just see how much line losses we might have with, say, 10 or 15 feet of piping, then let's just pop up a there we go. You just click on that and you've got the crane manual, and 250 gallons a minute is going to be down here somewhere. There we go. Can we zoom in here? Maybe. I love how fast this computer is. Here we go. Okay, 250 gallons a minute. This is the velocity, that's the pressure drop. So too high velocity, too high, too high, too high, too high. Getting warmer. We want to be around there. There's 3 feet per second, 0.195 psi per 100 feet. What size line is that? 6-inch line. All this stuff isn't that big at all. I think I'm going to go really conservative because it's a short line, and I'm going to go right to an 8-inch line, not fool around. Could do 6-inch, but I'm going to do an 8-inch. And so my pressure drop is 0.061. I lost my line there. Third one down, was it? Second one down. 0.051 psi per 100 feet. psi per 100 feet times what we think we're going to have in line losses here, or time, number of feet. So let's say we have 10 feet. We're going to multiply that by 4 for elbows and things like that, so 40 feet. So correction for elbows, multiplier for elbows, maybe it's a better way to say that. Elbows, strainers, valves, manual valves, et cetera, et cetera, et cetera. Okay, and so .051. So our delta P 0.02 psi, which means that a more accurate version of that source pressure is 14.7 minus 0.02 psi equals 14.68 psi. My assumption was pretty close. So there's my inlet pressure to the pump, 14.68 psi, aka 14.7. What about the what, sorry? Yes, that's right. There is an elevation difference there. That's a good point, Josh. Thanks. Yep. Okay, so the delta P, the elevation. Okay, so that's rho GH. Keeping me honest, that's good. So that's 10 feet times 0.43352. That's my conversion factor. The density of water is 1, so I don't need to correct for that. So that is obviously 4.3 psi in elevation losses. So now my new inlet pressure, which is the right one, is, whoops, did that wrong, 10.3. Okay, so good thing you caught that on me. Thank you. 10.38 psi. Psi A. On to number 4. Which is the discharge pressure. So our destination pressure down there is 0 psig, because it's an open pond. Our line losses. Okay, so now we want to try and run a smaller line because this is costing us some serious money here. So we want to go back to our line sizing here and look for something a little bit more aggressive here. We could probably look at that velocity. That would be a 4-inch line. So, and a 4-inch line could easily go up in terms of pressure. We could probably push it up into sort of 300 gallons a minute if we needed to. So that might be a reasonable way to go. Since it is a main header into a system like this, and we might end up needing a lot of water to fill the ponds initially, that's not something I'm really considering at this point in time, but we might actually want to run maybe a 6-inch line just so that we can push up in terms of higher flow rates for filling and things like that. So maybe what we should do is be thinking about a 6-inch line here. Normally I would have just gone straight for the 4-inch line, but this is I think a special case. So we might even go back and rethink that a little bit more and try and come up with what's a reasonable filling rate for the ponds. We know roughly what the volume of the ponds is, and say we want to fill it over the course of a week or 2 weeks or something like that, a long period of time, because it's a lot of water, and then go back and recalculate what another reasonable flow rate would be for special cases. For now, I think I'll go with a 6-inch line. And my 6-inch line has 0.2 psi per 100 feet. And we have 46.02 meters. 3.28. So we have about 15,000 feet. So our line losses are 15,100 feet times 0.2 psi per 100 feet. So we have about 30 psi of line losses. Now, we should put that 4 multiplier in there to cover all the elbows, all the tees, all that kind of good stuff. That might be a little excessive for this because we've got so many just straight lines without having, we're not really going to have as many elbows in there as we would normally have. So maybe what we should do is, well, for worst case, let's put it in there anyway. I think this is a good situation where you might actually go back and do this line hydraulics rigorously. So sit down with the program, put the number of elbows in, get a better design. We've got a really good design there. Elbows and valves, etc. We could easily do this a lot more accurately because that goes up to 120 psi. My engineering intuition is telling me this should be, actually, you know what? It's probably not far off. So we're gonna need some control valves up by the ponds here. I'd forgotten about. There's going to be level valves up on the ponds. So if I can imagine that's a pretty good pressure for the discharge pressure of the pump. I'm going to change this to a 1.5 factor. And so that's going to be about 45 psi in the lines alone. So that's what my intuition is telling me. But seriously, I would sit down and just do this rigorously. We've got a good 3D model layout. I would throw it into a pressure drop program and actually calculate this properly. That's my advice to you guys for something like this. Okay, other things we have flow elements. We have one, and so they're about 3 psi. It's probably reasonable. We're going to have control valves. So a bunch of different ways to do the control valves here. Let's see if we can pop up the okay, control valves, tools and programs. Is it opening? Okay, so we have 250. And we'll just go with the standard sort of D ratings on this one for now. That actually could go down a little bit there. Pump suction pressure is right around minus about 10, minus 5, roughly. Specific gravity is 1. Destination pressure is basically 0. And our static head, we said, is, what is that static head? 263. Okay, so 310 minus 263. So 47 feet of static head. Sounds about right. Frictional losses, we're saying about 45 pounds in frictional losses. I'm going to go with an 1800 RPM pump. And our control valve guess value, we'll say, is 25 pounds for now. So right off the bat, Connell's telling me I need 30 pounds across my control valve here. So we could go with that if we wanted. Let's try a couple different ways here. Control valve, 30 psi for Connell's method. I don't think it needs to be that much. Let's see here. Okay, so an estimate of the pump differential pressure at low flow and high flow, it's probably is not bad. And essentially what we need to do is goal seek the control valve pressure drop so that that ratio is 10. Let's just go up in pressure here. Just, you gotta get actually calculate a number there. Okay, so 50, 60. What's going wrong? 40 for a second here. There we go. I gotta go down. Okay, so we can just goal seek this if we want. Where's the goal seek here? Analysis. You guys know how to use goal. I'm sure you guys know how to use goal seek, right? So we want to goal seek that number to 10 by changing the control valve guess value. There we go. My method says 37 psi to get the kind of control range that we're looking there. So we got a choice. We got a decision to make there. Either we want to revise our min and max flow rates, or we go with one of those pressure drops. If we went up to say, I don't know whether this is going to actually happen or not, but say 300 gallons a minute, 600 gallons a minute or something like that, then this pressure drop guess value is probably going to have to go up, I think. It's going to have to go up a lot. Yeah. Wow. So if we really want to get that kind of flow rate, we're going to need multiple pumps, I'd say, because we don't want to put that across a control valve. Okay, so that's not what we want to do. That helps, actually. And we'll go back to, say, 37 pounds or whatever it was. Yeah, okay, so I'm going to put 37 pounds. Gee, it seems high, but anyway, I'll go with my method with 37 pounds across the control valve and see if I missed anything else. We're still good for tape, James? Okay. So flow element. Oh, we've got another level valve here that we need to account for a little bit there. So I'm going to just assume that we're going to have 10 pounds across that other control valve for level valve on the pond. I think that's it, right? We need some flow elements. We've got one flow element there. Oh yeah, we've got two flow elements, right? Okay. So that's going to be 6 at 3 psi per. Actually, you know what? I'm just thinking about this. The flow rate in this section of the line here is actually a lot higher than this flow rate. So in reality, what we should be doing is we should actually stop and redo the calculations from this point forwards. Like we're going to have a different line size for that. And it will probably have a slightly different pressure drop per 100 feet. Everything else will be basically the same. The elevation losses are the same and all that good stuff. Maybe we'll rip through this way for now, and then we can go back and just check to see how much difference that would be when we added the flow rate in and resized that line. So the frictional losses may not change too much in the line, so it may not affect our pump size too much. But definitely there's a much bigger line size that needs to run around the ponds. Okay, so let's just add that all up. So we have 45 there, another 6 here, 37 here, and another 10 there. So we have 98. 98 PSIG on the discharge of the pump. We're actually getting really close to be done. Okay, so we got the discharge pressure. Now we need the shaft power here. Because I'm running out of space. Okay, so the hydraulic horsepower is equal to the flow rate in GPM, 249, times the delta P, which is 98 PSIG minus, and this is minus 4.3 PSIG minus 4.3 PSI, 3.2 PSIG, all over 1714. That's the conversion factor. So 98, add that, 249, 1714. And it comes out at being actually really small. Wow, that's really surprising. It's only 15 horsepower, hydraulic horsepower. Let's say the efficiency is, say 50%. So the brake horsepower, or shaft horsepower, is equal to 15 horsepower divided by 50%. Giving me about 30 horsepower, and that's actually not a very big pump. Did I do that right? 249, 103 roughly, 1714. Yep. That's all you really need in order to get a pump. Now you can go shopping for the pump if you want. And where is that here? Oh, let's hope it remembers my password because I can't remember what it is. Let's hope this works. Not sure whether it will or not. It's going to need a password, and I can't remember what my password is now. Maybe. Give it a minute to chug away there. Okay, so while it's chugging away there, the NPSH calculations for this one are relatively quick. What we need is the vapor pressure of the water. We need to take a worst case scenario. Like obviously the lake water temperature is changing throughout the year. We need a worst case scenario. So possibly if they drew it from deep enough, the temperature wouldn't change too much, but I think you probably want to count on something like 15 degrees as a worst case. Water. You know what, this actually might work better in Internet Explorer for me. Okay, so we need the vapor pressure of 15 degrees C water. We can do that really quickly with HYSYS, because that doesn't seem like it's working very well for me, does it? Whoa, what happened there? Okay, so if we want the vapor pressure of a stream, let's just pop up HYSYS and do it real quick. I just need a stream. I just need to tell that it's water. Whoops, that's not right. Ah. Okay, there we go. And we want it at 15 degrees. And we want to just set it right at its dew point. And there's the vapor pressure right there, 1.7, otherwise known as 0.247 psia. Okay, so my, I'll do it right here, so it's on the same board. NPSH available. Still okay for tape? 10 minutes? Okay, cool. Okay, so what I need is the difference between the vapor pressure and the actual pressure at the pump. So my actual pressure is 10.38. Minus the vapor pressure, which is 0.247 psia. Okay, because I've accounted for all my line losses and stuff like that in here already. So that makes that fairly simple. And the difference is 10 point, whatever it is. So 10.1 psia, and then we just basically convert that into feet with rho GH. So I just take 0.43352 divided by that, so 10.13 divided by 0.43352, and the specific gravity, which is 1. And we get 23.4, 23.37 feet of liquid. So we're looking for a pump that requires less than 23.4 feet of NPSH. And actually what we probably want to do is put a 1.2 multiplier on there, because we want either minimum of 3 feet or 20%. So that's available So the pump we picked should have an NPSH required of 28 feet or more. You should say greater than 28 feet. It's a better way to do it. And let's see if this ever popped up for us or not. It doesn't look like it actually happened for us, did it? I find sometimes Internet Explorer is actually better for this. Let's try Internet Explorer and see if we can get it to work. If not, we'll do it on the VDI, because I think the VDI. Let's see if that works. Should pop up with a little dialog box here with your password requirements. Takes a minute sometimes. Questions? Yeah, Jeff.
For the line losses, what do we use if we're not using water? Like this one was the grain manual, but for all the other ones, do we just assume that it has the same losses as water would?
You got to make a judgment call. You can either do that, or you can pop up HYSYS and put a pipe segment in and do the pressure drop calculations in HYSYS. So that's not terribly hard to do. Whoops. Where is that pipe segment now? Lost it in the new version. There it is. So you can do that. And then you can actually try different viscosities if you want. Because you're able to, I haven't done this in ages, you guys. I forget how to do this. I got to go look at it. There it is. That's what we're trying to do. So you add a segment, append a segment there, and then basically you can put your elevations in, and somewhere in here is a way to put fittings in. Yeah, you can get fairly complicated with this, but all you really need is put 100 feet of pipe in there, and put your fluid in, and calculate the pressure drop per 100 feet of piping, and then you can use these rules of thumb. So that's a quick way to do it. Yep. Okay. I think we're pretty much done anyway, except for the pump sizing selector. Yeah. Oh, okay. We got 4 minutes. We'll just let it run. Yeah. Any other questions? So what you can do is just look at your viscosity and see if your viscosity is roughly close to water, and then you can decide whether you want to use the crane tables or not. Yeah. Any other good questions? Is that helpful at all, or? Yeah, a little bit. Okay. I was thinking of kind of doing the reactor one as well, but it's pretty straightforward. Oh, the only thing I was going to kind of maybe make as an extension, we can do it after the tape runs out, is maybe have a look at what would happen once we bring the raceway return in, because that's going to be the majority of the water flowing around is that raceway return for sure. How I would handle that. So very, very simply, I would just put expand the pipe right here, and look at the combined flow rate that's needed there, and just recalculate just check my frictional losses through there. I'm pretty sure the frictional losses won't change very much from there, because you as the process engineers have the ability to just change the diameter, so you can almost almost pick whatever frictional losses you want because you get to pick the pipe diameter. I'll try and get the pump sizing selector working as well. Not sure why that's not working on my computer, but I guess it's not surprising on mine. Any other questions before we wrap it up? Okay, well, that's it then, guys. Thanks very much for coming in this morning.